Okay, this will be the last of the videos for today, and I want to talk about zero padding sequences. Okay. So the traditional FFT algorithm required that n be a power of 2. Okay. So if n is not a power of 2, we can zero pad our sequences to n bar that is a power of 2 that's greater than our sequence length. So like in that last example, I did a DFT with a sequence length of n. In the traditional FFT algorithm, I'd have to add zeros onto that sequence to bring it out to a length of 128 in order to use the traditional FFT algorithm. Now, MATLAB's FFT algorithm is really a DFT, but if you actually do some timings on DFT lengths, you'll see that if the sequence is a power of 2, that the FFT algorithm in MATLAB is much faster, maybe 100 times faster or more. It actually depends on the sequence length. Than sequence lengths that are not power of 2. There is another reason to use zero padding, not only for the speed, and you're required to, but what zero padding does, it gives us more samples of the underlying discrete time Fourier transform. Now, we haven't talked about this yet, and we'll talk about it in a later chapter, but the DFT actually gives us samples of an underlying discrete time Fourier transform of the sequence. So it gives us, with the more samples, we have a better picture of what the discrete time Fourier transform looks like of the n length sequence. Now, because we're using a sequence of length n bar, our bin spacing will change. Our bin spacing will now be fs divided by n bar instead of fs divided by n. And since n bar is greater than n, our samples in our spectra will be closer together. So let's look at an example on the slide. This is from the textbook. It's figure 411, and it illustrates zero padding a sequence out to a power of 2. So let me flip over to the slides, advance to the next slide. So in this particular case, they had a short sequence of 12 samples. I think it actually consisted of, I forget now, a sum of a couple different sinusoidal components. And so here's the underlying, here's the DFT. Look like they use came from sampling a sequence at 100 hertz rate. Again, we see the symmetry about the midpoint here, and that the magnitudes are the same. And then here they've zero padded out to a power of 2. They've gone to 12 to 16. And so it takes the original sequence and then just adds 4 zeros to the sequence. So that's really easy to do in Octave. And then now we'll get 16 samples in our DFT as well. So samples with a different frequency resolution, 100 divided by 16 instead of 100 divided by 12 here. So we could continue this. Here they've added 20 zeros, so they've gone out to the next power of 2, which is 32, and so they have corresponding 32 samples in the frequency domain. So here we get a little better picture of what the underlying discrete time Fourier transform looks like. Now, we'll find later that when we're trying to resolve two frequency components that are close together in frequency, in order to do that, in order to increase the resolution, we actually need to use more data. Zero padding won't help in that instance. That we actually have to have a longer original data sequence, and then we can pad it out to the next power of 2 for convenience if we want. But zero padding doesn't actually help us resolve two frequency components that are close together. We need a longer data sequence in order to do that. So this example kind of showed padding out to a power of 2. I had another one here showing 12 samples in the original case, and then the corresponding DTFT. And then in this next one, I actually padded with 12 zeros, so we had 24 samples, so we'll have twice as many samples in the frequency domain. But the reason I did this is that if you look, you can see that every other sample now is exactly equal to the sample in the previous picture. So 0, skip, 0, 0, 0, skip. These are all samples that are exactly equal to the case where we padded with I doubled the size. Here I quadrupled the size. Again, you'll see all of these samples from the previous XK appear here, but now we have additional kind of interpolated samples between those. So zero padding in this case, I'm just trying to illustrate, it's not really adding any new information. It's just kind of filling in the gaps between our samples. So it's a useful thing to do. And again, there's an M file here that I'll make available. It's called zpad example that you can run to see this. I will note, I think, too, that if you compare my results in Figure 11 to those in the textbook, my amplitude spectra is scaled differently. He actually makes a mistake there. And to get his amplitude spectra, he divides by the FFT length. That's not correct. You're actually supposed to always divide by the length of non-zero samples that you have. So you're supposed to divide by 12 in order to get the amplitude spectra. And finally, let me mention, before I do this last example, that you could, let's say we have a sequence in octave that's 1, 2, 3, 4, and of course that's a power of 2. But let's say we want to zero pad out to the next power of 2. You could do this, use the zeros function, 1, and then add 4 zeros. Okay, and then just do x is equal to FFT of x. Okay, and then this will do an 8-point DFT. You don't have to do that in octave. Instead, what you can do is 1, 2, 3, 4, and then if I call FFT with just the x argument, it'll do an FFT using 4 points, but I can pass it a second argument, like 8 in this case, and that's equivalent to zero padding x and then doing the 8-point DFT. So this would actually do zero pad x and then do the FFT for me. So I could actually say that I want a 32-point DFT, and it will add 28 zeros to it, or 64-point DFT, and it will add 60 zeros to it, 64 points to it automatically. There's one final example I want to look at. This is an example from the textbook. So here they have a sinusoid that's at 1,000 hertz, so 2 pi 1,000 at a sampling rate of 8,000 hertz. Okay, and so so this is the sequence obtained from sampling this continuous time sinusoid, and then let's see. We're going to use the MATLAB DFT to compute the spectrum, so the resolution is 8 hertz. So there we we want a resolution of 8 hertz. So we divide our 8,000 by 8, and then so we want to use an n value of 1,000. That's part A. And so if you do that, this is what you get for the amplitude spectra. And notice we get the frequency component at 1,000 is clearly shown. We get the kind of the replica that appears at 8,000 minus 7,000. Again, we really only have frequencies up to the folding frequency, in this case 8,000 over 2. This is power spectra. Of course, in this case 1 squared would be 1. And let's see, this is showing the one-sided spectra. That's what this is. So we should get from the amplitude spectra directly, this has a height of 2. That should be the correspond to the amplitude of our sinusoidal component. Now, part B is 0 pad out to the next power of 2. And so again, you don't need to 0 pad with the DFT. We could directly do 1,000. If the FFT is used, we want to 0 pad out to the next power of 2, which is 1024. You could even pad out to 2048 to get additional samples. You'll find in this case that the FFT algorithm is much faster using 1024 samples than actually using 1,000 samples, but the frequency resolution is different. It's 8,000 divided by 1024, or there'd be 7.82125 hertz apart, instead of the what was it, 8 divided by 1,000, instead of the 8 hertz apart that we had in the previous figure. But you get similar information. Again, here's the amplitude spectra. Again, the spacing here is different between our XK values, but it shows up at the same corresponding frequency at 1,000 hertz in both the amplitude and power spectra. Then the next is just showing the one-sided spectra, and again clearly indicates that the amplitude of the sinusoidal component is actually 2. So that's it for today's lecture. We'll see if we have class on Wednesday. If not, I'll again post videos for the lecture. So check the website. Look under the lectures link. I'll post homework problems for today as well.